G'day, Chris here and welcome back to ClickSpring. One thing about this project is that there's certainly no shortage of wheel and pinion cutting. All up there are 10 wheels and 5 pinions, giving a total of 529 teeth to cut. The cutters, of course, were completed in the previous episode and are ready to go. So the next step is to prepare the raw sheet stock and cut out a set of appropriately sized blanks. A quick tap marks the centre point of each of the blanks, and then it's onto the scroll saw to separate them from the parent stock. The 72-tooth Eclipse idler wheel is the largest of the 10 wheels, and is a great place to get started on the wheel cutting. Now there are of course several ways to form gear teeth, one of the most common being to perform the whole task on the mill. As it happens, I tend to cut teeth almost exclusively on the lathe, and here's a close-up look at the setup that I use. It's all based around a Myford brand vertical slide that mounts to the lathe cross slide using this shop-made adapter plate system. There are 3 component plates that connect together to give a solid interface with the lathe and also securely hold the motor and speed control. An indicator is run across a reference face on the spindle to confirm squareness with the lathe axis, and then the motor and speed control are slotted into place. The T-slots in the plates are arranged to permit the motor and speed control to move relative to the cutting spindle, enabling the correct belt tension to be set no matter where that spindle may be on the vertical slide. The cutting arbor is then mounted into the spindle, and the cutter loaded and aligned square to the work. The lathe axis is identified using a centering button, and once the cutter is centered on that axis, the cross-slide hand wheel is zeroed to record the position. As a final step, the cutter is then raised above the workpiece, so that the motor and speed control can be positioned for a comfortable belt tension at the full depth of cut. The dividing equipment is next to be set up. Any type of indexing system that can be attached to the rear of the lathe spindle will be suitable, but as it happens, I have a CNC based indexer that is of course much more convenient. If you haven't seen it already, be sure to check out the full detail on how this all comes together in the Tools Glorious Tools series, episode number 2. To establish the full depth of cut with cycloidal cutters, the typical process is to first take ever-increasing cuts on each side of a single tooth, while keeping a close eye on the slowly disappearing marking out fluid at the crest of the tooth. One thing to keep in mind while doing this is that the radius of the fly cutter arc is likely to be a bit larger than a commercial cutter, and so the risk of accidentally running it into the chuck is increased. A carriage stop is a reliable way to prevent this from happening. The correct depth of cut has been reached when the barest hint of marking colour remains at the crest of the tooth. The vertical slide is then firmly locked off, and the full wheel cutting can then proceed for all teeth. You might have noticed that I'm keeping the feed-in rate of the cutter quite low. Typically, a commercially made multi-tooth wheel cutter has 12 teeth. Those cutters can be run at maximum RPM and will provide a high-grade surface finish without requiring particularly careful feed management. But fly cutters have a single tooth and so can only make 1 cut per revolution, so the feed rate needs to be significantly reduced to ensure a decent surface finish to the cut, with the slow and consistent feed of the cutter into the work being the key to getting the best result. Surface finish aside, it's also not a bad idea to be quite gentle with a fly cutter, just to avoid the risk of breaking it. A gentle heat from the torch breaks the superglue bond, and that wheel is done for now. The arbor can then be refaced and trimmed to accept the next wheel, or if it's a big step change in diameter, the arbor can be swapped out for a size better suited to the diameter of the next wheel to be cut. Some of the wheels require trimming to a final thickness less than the original raw stock, and some require a small shoulder to be formed. In that latter case, another version of the centering button is a great way to help with the marking out. As I mentioned in the previous episode, turned fly cutters throw up a small burr around the exit of the cut. 800 grit abrasive paper will knock them down easily and clean up the tooth profile. Okay, so that's 8 of the required 10 wheels. For maximum concentricity with their mating parts, the remaining 2 wheels will be cut later in this video, as I form the Lunar node display assemblies. So for now, that's the wheel cutting complete. Next up are the pinions, which aside from being cut from rod stock, are formed in essentially the same way. The one big difference to wheel cutting is that I found it helpful to do a rough stock removal pass prior to the final cut. It reduces the load on the cutters and also reduces the workpiece deflection, in this case removing the need for tailstock support entirely. Once parted off, each pinion must be brought to its final length dimension, and for that, a simple friction fit arbor is suitable. A piece of brass is turned to a light interference fit with the inside bore of each of the pinions, and then the required cuts are made. Okay, so with most of the wheel and pinion cutting complete, it's time to have a look at some of the more complex assemblies within the mechanism. Each of the lunar and solar zodiac display assemblies consist of 2 concentric sub-assemblies. The inner structure indicates the position of the sun and moon in the ecliptic, and the outer assembly displays the position of the lunar nodes in the ecliptic. For these assemblies to function correctly, it's not only important that the parts be formed to the correct dimensions, but also that concentricity be maintained between the mating sub-assemblies throughout the fabrication process. I'd also like to make the best use of the raw stock that I have on hand, and the time spent on setting up and then breaking down machining setups. So in this part of the build, I conducted the operations in a specific order. The process started with this section of brass stock that provided 3 of the required components, the first of which is one of the lunar node display discs. For simplicity, I've designed both discs to have the same dimensions and profile, although they'll have different markings etched onto them later to distinguish them once installed within the mechanism. A simple gauge helps ensure the running fit required for these parts, and the centre hole is drilled and then reamed to give a close fit on its mounting arbor. The second display disc was formed using the other end of the stock, much like the first. And you may notice that I've left both of these parts a little long at both ends. I'll talk about why that's worth doing later in the video. Now it's often very hard to avoid ending up with the chucking portion of a piece of stock as a leftover at the end of making a part, which for something as expensive as brass is less than ideal. The offcut usually goes into the scrap box to hopefully get used at a later date. but in this project it can be put to immediate good use. With a trimmed reference surface, it can easily be bonded to a superglue arbor and then turned into one of the Lunar display wheels later in the process. So after a light trim of the parted surface on the display discs, that's 2 roughed out components and the raw stock for a third, all from that single section of brass. Next up are the Lunar node display rings. This recessed arbor is perfect for the next couple of operations, for both holding the blanks for trimming their outside diameter and also permitting easy boring of their centre hole. First, the perimeter of each blank can be tidied up and the centre holes bored to final dimension. But for maximum concentricity, all of the other features will be left until the blanks are in position on their respective node display wheels. So for now, that's the 2 node display rings roughed out and ready for further turning later. Next, I made the wheels on which they'll be fastened, what I'm calling the node display wheels. Essentially, they're a standard wheel with a boss formed on one side to accept the node display rings. And again, a simple recessed arbor is a convenient way to hold the work while forming the features. That offcut from earlier in the video was the first to be bonded in place and then turned to the correct outside diameter for wheel cutting. The wheel cutting equipment was then installed on the lathe and aligned with the centre of the work in preparation for cutting the teeth. I've designed the boss section on the wheel to be an interference fit with the node display ring, but it could just as easily be bonded in place with a modern adhesive or soft solder if you prefer. The features of the Lunar node display ring were formed next, using the display disc to confirm the correct diameter of the recess. When it comes to removing the workpiece from the arbor, heat will of course break the superglue bond. An alternative, if time permits, is to soak the parts off using acetone. It's a great way to remove a part that may otherwise be sensitive to being heated. The other node display wheel was formed in much the same way as the first. Again, the node display ring blank was pressed into place, and then the other features were formed. One difference between this and the previous display ring is that in this case the design calls for some angular markings. If still attached to the lathe, the wheel division equipment is of course suitable for the job, but the angle is not super critical, so any reasonably precise marking technique would be okay. There will be some etching and silvering of these parts later in the build, but for now these two sub-assemblies are done for the time being. Now I mentioned earlier that I'd left the node display discs slightly long. To some extent they're designed to sit proud of the face of the mechanism, although that's a matter of personal taste. They could certainly be trimmed flush if preferred. But by leaving them long during fabrication, it means that the clearances of these assemblies can be set quite close, without having to be overly precise when forming the recesses and shoulders. Once a display disc is mounted onto a superglue arbor and its matching node display ring is loosely fitted onto the boss, you can see the extra material that needs to be removed. There's also a similar amount of material to be removed from the other end. But in each case, using this method, it becomes quite a straightforward job and can essentially be done by eye, trimming and checking while using a flat reference surface like a parallel until the desired end shake is observed. The same techniques can be applied to each of these sub-assemblies, and it greatly simplifies what would otherwise be a more difficult task of managing the various shoulder and recess dimensions to achieve a consistent end shake across both sub-assemblies. Now strictly speaking, I could leave the other end of the display discs in that long condition until later in the build. And there's something to be said for leaving a little bit of extra material on this face until I know just how thick the front dial plate will be once it's fabricated. But I'd like to show you another useful variant of the superglue arbor, as described in the many books by the clockmaker Bill Smith. This version, with a consumable brass rod running down the centre, is particularly useful for relocating a workpiece back onto a lathe axis. In this case, the hole in the component that I'd like to relocate on the lathe is 1/2 inch. So the rod is extended and a matching 1/2 inch spigot is formed on the end, that of course now sits true on the axis of the lathe. This becomes the register on which to locate the part. The grub screw holding the rod in place is loosened and the rod is tapped out of the way, permitting other parts to be bonded into place as required. All components are now well aligned on the lathe axis and registered with each other, setting up the required condition for whatever operations are required to follow. Like so many of the techniques taught in Bill's wonderful clockmaking books, it's an incredibly useful idea. And if you haven't seen Bill Smith's books, be sure to check them out. I'll put a link below. The final components required to complete the assemblies are the two arbors, which were formed on the lathe from mild steel. The wheels will be permanently bonded to these arbors later in the build, but for now it's helpful to keep everything separate to permit convenient depthing. The parts can, however, still be brought together for a dry assembly to confirm clearances and to permit a close examination of their overall fit. In the next video, the mechanism will continue to take shape, as I complete the rest of the assemblies for the gear train and also make the bowl and the front dial plate. Thanks for watching. I'll see you later.